Good morning again, the four ladies and gentlemen, as I counted well, I hope. We have four ladies in the room. Welcome. So we will carry on riding on the Hacktivity bicycle today with this session here upstairs with our speaker Adrian Furtuna from Bucharest, Romania. Am I right? Okay. And I suppose we will have a very interesting presentation right now. Adrian currently works as a security consultant and involved a lot of penetration projects against web applications, mobile applications, and network infrastructures. He's also a lecturer in several master programs in Bucharest universities, teaching the practical aspects of system security testing. He's also founder of pentesttools.com. Hopefully you will speak about that, at least one sentence. In this presentation, he will show us a method of automating challenge typing and response reading from a Digipass device, I think. Don't spoil the fun. Okay, I don't speak anymore. I think he will tell you the story. So, Adrian, please.
Thank you. Am I speaking loud enough? It's okay? It's okay. So thank you for the introduction. Thank you all for being here today. The things that haven't been said about me until now. I'm 30 years old. I'm married. It's my first time at Hacktivity, but not my first time in Budapest. I've been here before and I find it a really nice city. So I recommend all of you who haven't seen the city yet to go and visit, after the conference, of course. What are we going to talk about today is something about fun and profit. And when I say profit, I'm referring to financial profit. And the fun part, I had fun with it. Hope you will too. I also have a PhD in information security and a CH, but this is not too relevant. I do pen testing at KPMG Romania, and I always like to prove my point. This means that whenever I find some vulnerability or something that it's not right, I want to actually give a proof that that the vulnerability exists and it is real, as most concrete as possible. What is this all about? Let's start with the fun part of the presentation. Long story short, I have built this device, which you can also see on the desk. Any ideas what it does, what it looks like from just looking? Sorry? Yeah. Yeah, you got it almost right. Your colleagues here said it's a pin typing machine. Yeah, my friends told me it looked like a bomb, but it's not really. It's not going to explode or something. But I had some hard time explaining this to the airport control guys, which looked at it very carefully and put me to do some heavy explanation. But I finally passed over it. What you see there, down there, it's one of these. These are called Digipasses or security tokens. You see that they have a keyboard and a LCD display screen. So this machine applies to all these types of tokens. So can be modified a little bit to apply to all these tokens. They are mainly used for user authentication. So what they do, you start them and enter a PIN code, and then they generate a unique number, which is correlated on the server side of the internet banking application. And the bank knows that it's you, the person who wants to authenticate, because only you have that specific device with a specific code associated with your name. Another utility for these devices is to sign transactions in internet banking applications. This means that you enter a challenge code and the device gives you a response code back. Some common vendors for these types of devices: Vasco, CryptoCard, RSA, and others. So what is this really all about? This is a highly experimental device. It's built at home by myself, a prototype you could call it. It's a machine that simulates human behavior when using a Digipass. So imagine yourself, you want to do an internet banking transaction, you have a Digipass like this, and you define the transaction, and you cannot submit it until you sign the transaction with one of these. So imagine yourself, you have your brain which commands the movements of your body, of all your muscles. Your brain tells you to move the finger over the start button, to push it down, to release it. Your brain sends electric signals through your neuronal system to your muscles to do anything they want. And you also have your eyes to see the results of the movements that you make. This was what I was trying to do. In our scenario, the brain is a piece of software written in C, which commands the whole machine, selects the desired muscles, keeps the track of the logic state, interprets the image read by the eyes. We also have the neuronal system, which is the electronic circuit. It's a very basic circuit. I'm not an electronics expert, but I got it working. They actually transport the signal from the brains to the muscles. These are the muscles. They are called solenoids. They are a special type of electromagnets, which when they receive power on these two wires, they actually push this stick down for a few millimeters. And when you cut the power, the stick is released. So they actually transform electric energy into mechanical energy. And we also have the eyes, which is a plain web camera, which reads images that this device outputs on the LCD screen. Okay, right now you'd say, nice, Adrian, you have built this machine, but why? Why would someone build such a device for typing keys instead of himself? For myself, actually, the motivation was to prove my point. But for others would be to actually gain some financial interest. No? Let's go to the profit part of the presentation. If you remember the rounding attacks against internet banking applications, this is not a new type of attack. It's actually, someone has written about it since 2001. And a very good recent article from this year was published by a guy from a cross-security blog. What it is actually, it applies to internet banking applications which use 2 decimals for showing the values that you have into your account. This means that if you somehow manage to transfer into your account a value with, let's say, 4 decimals, this will be rounded to the closest to decimals value. Okay? So you see, if you have a value above here, 3, 4, 5, if it's above 3, 4, 5, it will be rounded to 3, 5. It is below, if it is below 3, 4, 5, it will be rounded to the lowest value, 3, 4. So if you actually manage to transfer yourself this exact amount into your account, you will gain 0.0022 euros from the rounding. So the maximum amount that you can gain from this type of rounding is 0.005 euro. It's not a huge amount, of course, but one thing is that it can only be done with electronic systems. Imagine that you go directly in person to the bank. You cannot physically give this amount with too many decimals. But using electronic systems like internet banking applications, this can be done. So practically, this applies when you have an internet banking account to your bank and you have 2 accounts of your own. For instance, one in forints and one in euros. We made this, so this talk comes after a penetration test that we have done to an internet banking application in Romania. And we discovered that the application was vulnerable to this issue of rounding attacks. And we actually managed to transfer money from a RON account, which is the Romanian currency, into euros at a much better exchange rate than the official exchange rate. So we had 2 accounts, one RON account and one euro account. And usually the exchange rate was 4.4. When you exchange 4.4 RONs into euros, you should get 1 euro. No. You should get 1 euro, right? But what happens if you try to exchange a lower value? So as the value that you try to exchange goes down, the rounding is more in favor of you. So for instance, if we go to 0.03 RONs, this will be exchanged really into 0.0068, which will be rounded to 0.01. The lowest amount that we could exchange was 0.023, which was exchanged into this value. And we had actually the exchange rate to 2.3. If we went below this value, the final value would get rounded to 0, and it would not be in our favor. So imagine if you do 100 of these micro transactions, you could gain from 2.3 RONs 1 euro. In the conditions when 4.4 RONs was 1 euro. But you have to do 100 these types of transactions. This is a screenshot from the actual internet banking application. Is from the the area where you can see your transactions from your account. You see this was the euro account. And you see the lowest value that we could exchange was 0.02 was free here. And the official exchange rate 4.4. And you see that the account was loaded with 0.01 euro. You can actually test this yourself in your own internet banking application to see if it is vulnerable to this or not. I have made a calculation also for forints. I didn't actually test this, but when I did this calculation, one forint was 283. 1 euro was 283 forints. This was the official exchange rate. And if you try to exchange a lower value, the best value that I could find was 1.42 forints. If you exchange them, you gain 0.01 euros. This means an exchange rate of 142, comparing to 283, the official exchange rate. Okay. Now we went to the bank, wrote the report with the other findings. We presented them this finding, and they said, we know about this issue. We know about it, but there are roundings that are made in our favor also. So given a high amount of transactions, it should be a draw. And we told them, no, this is not true, because a malicious person could intentionally exchange to to make roundings in his favor. They said, okay, it's true that, but we have this Digipass. So there is no way a person can do thousands of transactions manually. Enter the code, read the response, send it into internet banking application, and so on. And then I said, you're wrong again. I can prove it to you. So I took it more as a personal challenge. And they were surprised what it came out at the end. In the normal course of making a transaction, what you have to do, a user enters the internet banking application, initiates a currency exchange operation. The application sends you a challenge code. You have to type the challenge code manually into that device, which is unique for you. The device responds with a response code. You have to read the response and send it to type it into the internet banking application manually. Right now, this phase, which should have been made manually, can be automated with this device. This means that we can do lots of transactions automatically. So this device is a protection, but it's not bulletproof. Okay, now how much money we could earn using this vulnerability? The schema that I see is this one. So you have an initial amount of your currency. You exchange it into euros using lots of microtransactions. Then you exchange it back to your currency using a single transaction at the official exchange rate. So I have made some calculations here, and the final amount equals the initial amount multiplied by a multiplication rate. And you can also see the number of transactions required. So to see an example, if in the RON case, the multiplication rate was 1.9, in the foreign trades case was 2. So you actually, in the foreign case, you actually double your initial amount using microtransactions. But you have to do lots of microtransactions. So if you have an initial amount of 5,800 forints, you can double them by doing 4,000 microtransactions. Okay, this means gaining 20 euros out of nothing. Okay. How the banks should protect themselves if they are vulnerable to this issue. One of the things is to limit the minimum currency amount that can be exchanged in a transaction. So do not let the user exchange 0.0 RONs into euros, because it doesn't make sense really. Another thing would be to limit the number of transactions that a regular person can perform in a certain amount of time. Also, the bank should monitor for suspicious transactions, very small amounts, and state in the contract that such transactions are illegal. There is a whole discussion about this, if it's legal or not. We'll talk about it later. Or another thing is to introduce a small fee when doing a certain exchange. Just a small remark here. When we went to the bank with the report, the initial report, and told them about the vulnerability, I've told you what was their reaction. After a few weeks, after I've built the machine, we showed them the machine. And the guys who were responsible with the internet banking application said, by tomorrow it has to be fixed. So, so it had a really high impact. So proving your point is really important. And we indeed tested again the application, and they used the first recommendation here. They limited the minimum currency that can be exchanged in one transaction. Okay, let's go back to the fun part. So when I started this little project, I had two approaches. I could have done an internal instrumentation or this external instrumentation. The internal instrumentation, what I mean about it, is to do direct electrical connections on the circuits of this device. First of all, when I told the guys, when I talked to a few guys from the bank that I'm going to do this thing, they said, you're not going to be able to unlock that, to open it, because it will deactivate. It was wrong. It didn't deactivate. I read somewhere on the internet that there are Digipasses that even explode or do something when you try to open them up. But imagine that the bank didn't buy the most expensive Digipasses for their clients. They bought the cheapest ones. So it works if you open them. One condition is to maintain the power. So that's my finger over there. So if I try to do internal instrumentation, it had some pros. It could have been more reliable and faster, almost error-free, I guess. But I think it would have been very difficult to do. First of all, might not always be possible with all models of Digipasses. You must know the configuration of pins of this LCD screen. I didn't know the producer. I didn't find any technical specification on the internet about the LCD screen. and it had, I think, more than 60 pins. So it was pretty difficult to try and hook yourself directly on those pins. Another thing, sensitive soldering would have been needed. So I chose this external instrumentation, and I think the biggest advantage of this approach is that it is applicable to any model of Digipass which has a keyboard and an LCD screen. So you just change the configuration of these solenoids and it will work. It has also some disadvantages. These mechanical devices sometimes fail. They do not always work as you expect. And another thing, it was built at home. A more professional build of this device, I think it would work better. Another disadvantage of this approach is that I use a webcam to read the response of an LCD screen. I don't know if you have ever tried to do this, but it's not that simple as it seems, because there are all kinds of shadows and reflections of the light from the glass of the LCD screen, and it's not simple at all. But I finally got it working. Let's hope it will work here with these lights, but we'll try. This is the electrical diagram. I don't know if you see it. I wrote it in Visio, as you see. As I told you, I'm not an electronics expert, but I remembered the concepts that I've learned in the faculty, and I've just put them together to make something workable. These with M are these solenoids. These are transistors. And a circuit goes from here, from the plus, on this wire to the solenoids, through the transistor to the ground. In this path, the transistor acts as a switch, which by default is closed. So by default, the solenoid doesn't receive any power. In order to open the circuit, we need a current in the base of this transistor. And the current, we obtain it from this device, which is a multiplexer. I have 13 of these pairs, each corresponding to a key of the Digipass. What the multiplexer does, it receives 4 input signals on these pins, which are received through a parallel cable from that ancient machine. I tried hard to find a laptop with a parallel port, but it was the simplest approach that I could take. And depending on the configuration of these input signals, one of these output signals will be, output pins would be activated. So for instance, if I send on the input pins 0, 1, 0, 0, the S4 switch will be activated and will actually press the key number 3 on the Digipass. So it's not very complicated. Okay, let's go on. Now with the reading part of the response. You know optical character recognition, right? It's a software that you give it an image and it extracts the text from the image into a string, right? It should be right. It is right in theory, but in practice, it's much more difficult. This OCR software, I used GOCR and OCRAD, are from Linux. They expect a white background, a perfect background, ideal conditions in order to recognize the characters. As you see, the situation here is not ideal. I found some script on the internet which clears the background of an image and extracts the text. Okay, I thought that this would be the response to my question. So this is the text extracted from the initial image. What do you think? What do you think the OCR software will do? It will do nothing, because these are dots. This is not a continuous line. Even you as a human see it as a continuous line. It is not. These are dots. So the OCR software says, no, I don't know what is it. And I found a solution for this. I applied a blur to the image. And by blurring, I made the black points unify between themselves. And then I applied the threshold, and in order to select the black points with the value of black above a certain threshold. And this gave me a rather straight line in which OCR software could recognize the characters. You see that the result is strongly influenced on the lighting conditions of the initial image. So I'm very curious how it will react on these lighting conditions. But I can tell you from experience that you can find, I mean, it's easy to find a room with proper lighting conditions. Actually, you need diffuse light. So if you put a lightning bolt just on top of it, it will not work, because all you'll get reflections from the glass of the LCD screen. So you need diffuse light to come from all over the room. And you can find these conditions. I found them easily. But I don't think it will work here. We'll try. Current performance. In 6 seconds, it does a transaction. This means 10 transactions per minute. And when I say transaction, I mean pressing the sign button, introducing the 4-character PIN, pressing enter, entering the challenge code, and reading the response and doing OCR. This is one transaction that can be done in 6 seconds. So our previous example with 20 euros, to gain 20 euros, you will need about 7 hours and 14 minutes if you use RON, and 6 hours and 48 minutes if you use forints. In these conditions, one transaction in 6 seconds, you can maximum do 21,600 transactions per day, which means that maximum amount that you can multiply per day is 30,000 forints, or about 500 RONs, and you could gain about 100 euros per day by doing 21,600 transactions. Anyway, it's pretty hard to imagine that the bank will not observe these transactions. They probably will. But you cannot be sure about it. And there is always the low and slow approach. You do not have to do them all at once. And also imagine, what about banks that do not have this second factor authentication, that you only need the web interface to do a transaction. So you can do zillions of transactions per day in this case. So this Digipass is a protection against this attack, but it's not perfect. You can call it also a money-making machine. Photo gallery. These are the steps that I took for building the machine. This was the first proof of concept. Any idea what this box is from? No. It's a shoe sponge box. I just wanted to see if a solenoid like this can push the button and release it, if it works. Then I started building the machine piece by piece. So I cut all the things here. I did it from zero, from scratch. These are development stages. Okay, this is the final version from the back and final version from the front. Okay, now let's see if it works. As I said, with mechanical devices, there is always a chance that something will not work. But let's see. Okay, I have to plug it in first. This is what the web camera sees. Yeah. So what I do, I choose a random challenge code. I send it to the machine. And the machine does OCR, and this is the response that I get. As you see, it's not very accurate. There are some things that I can do, some empirical findings. So this thing is something that diffuses the light. And from what I see, the light comes stronger from there. And I can try to put this here. Almost. Yeah, the last digit, it's a little bit problematic. But I don't know if you see it there. Yeah, something like this. I can make it go stronger, faster if you want. So let's put it to the fastest mode. No. Just a minute. Can you help me to turn a little bit off the lights from there? It's okay. It's okay. Yeah, this is better. Something like this. Anyway, you can find proper conditions for the OCR to work. Okay, this was my presentation. If you want to see it, come and see it. Thank you very much for attending. And